and welcome to this talk about 10 years of automating Postgres. It's our recap. So let's see what happened. First of all, my name is Julian Fischer. I'm founder and CEO of anynines, a cloud and data service automation company. So 10 years. Well, actually, it's more than 15 years. So there's a 15-year birthday anniversary coming up this year for anynines. And in this talk, I'm sharing a few of the experiences collected automating Postgres along the way. So the talk is basically a chronological summary, and we're talking about different stages of automating Postgres and how the technological zeitgeist has affected Postgres automation over time. So the learnings are both the learnings of the greater tech community, but of course also my individual learnings as well as the learnings of my organization. So during this time period, we scaled from a few dozen to tens of thousands of virtual machines and containers being operated by us. That's not counting the assets under management where our automation is operated by customers. So how did this happen is what we are talking about in the remainder of the talk. But before we do that, I'd like to share a few of the aspects that we will be revisiting when looking at those different stages. So first of all, it's infrastructure. So there's a relationship between automation technology and infrastructure. So it makes a difference whether you primarily work on physical machines like we did back in 2008, or whether they are fully grown virtual infrastructures, so to say, programmable data centers. And this has also coined and forged automation technology. There's been a lot of improvement since declarative automation technologies showed up. And of course, it takes time to cover, all the aspects of lifecycle management of a particular software such as Postgres. So that also dramatically extended over time. As a metric to decide and show how effective a particular automation approach is, I'm using assets under management per DevOps. So a rough estimate on how many machines, whether it's a virtual machine, a physical machine, or a container, a particular full-time DevOps may roughly operate. Well, when I say operator, it's about the operational responsibility, which is something that changes too, because it makes a difference whether you hire a SysOp, a DBA, or a DevOps to run a particular database, or whether it's done by the application development team itself. And of course, this is a talk about Postgres. So Postgres changed over time, and we tried, various different approaches on how to, configure Postgres, and there were new Postgres features, and that also has impact on the way we automate it. So first of all, what I can share up front is a rough estimate on how many machines we've been managing over the years as an organization. So we started with a very few machines in the beginning, and with Chef we've been able to increase that quite a bit. But the tremendous increase in machines operated by us was basically with the emerge of declarative technology such as BOSH and Kubernetes. So throughout the remainder of the talks, we'll look at those different development stages, and I'll share some insights. So the era of imperative automation, it started at least for anynines in 2008 and 2009. We've been working with physical machines quite a lot. They provided very good performance for the Euro. And if you look at what these machines were doing and how they were dimensioned, assuming that there's a workload running that may spike and peak and have peak loads, you'd have to dimension the entire system according to that peak load because you've been unable to add servers dynamically. So ordering a server, adding it to a private network, a dedicated private network, was something that required days, if not weeks. Often you'd be bound to contracts um, once you order the server. So if you're on a customized data center, this could be even 2 or 3 years. So there was not much flexibility, and therefore most of the systems were over-dimensioned compared to the average workload. So most of the time, those servers were idle, which is a waste of hardware, of course. So another aspect was that a lot of these tasks, for example, extending a cluster, adding new machines, involves people in the data center. We never owned a data center, and therefore you're creating a dependency to an external company that will introduce unpredictable delays when executing particular tasks. So the automation was basically founded on shell scripts quite a lot. I mean, there have been automation and configuration management tools such as BCFG2, I guess, but this really never played a significant role in our organization. So the coverage of lifecycle management was basically about repetitive tasks, and a lot of the organization within the team evolved around how-tos written in a Wikipedia like wiki. Operating systems been managed manually. Software has been installed using operating system package managers where possible, and we compile software only where necessary. So in general, with that approach, you strive for a maximum of uptime of your servers, and whenever something goes wrong with the server, for example, there were hard disk failures quite often, especially when you buy clusters and they start to age and you bought them from the same batch. It's very likely that they will fail, that their components will fail in a short amount of time in groups. So at this time, you'll have to take down the server, involve people in the data center who will, hopefully have spare parts for it. And therefore you'd be looking at long time to repairs. This may happen during the night if it's a critical part of the system, which will then impact the sleep of the sysops. It's not a very pleasant experience. And with all the tasks you perform manually, there's an error rate involved, which will then cause problems and unpredictable um, efforts in the team. So you'd have to do the analysis, what's the root cause, and try to fix it. And all of that limits the amount of assets you can manage given a particular team size. So regarding Postgres at that time, especially because hardware failures impacted the availability of the system so much, we have investigated high availability options for Postgres and experiment with various different techniques on how to do that, including block level and file system replication, using tools such as Clusterverse, to just name one of many that we've tried. But eventually got to synchronous and asynchronous replication, which requires a cluster manager to be present if you want to have automatic failure detection and failover. So we spent much time with Pacemaker and CoroSync at that time. And that already improved the situation quite a lot, because the redundancy of a system, having a standby server that can take over a database to become the primary database in the event of failure, already mitigates that problem of being waked up at night quite a lot. But because servers were idle and there was a lot of waste ongoing, which also is a cost problem because not every company is able to afford building physical clusters. There was a lot of business that we couldn't handle because the clients, they had a need for, let's say, a redundant cluster where application servers are redundant, where database servers are redundant, but they just couldn't afford it. So with the introduction of virtual servers, talking about virtual machines based on technology such as SAN and KVM, there's an increased hardware utilization by achieving higher utilization of the machines by co-locating more virtual machines on a physical host while still maintaining a healthy isolation between those workloads. So you could basically co-locate application servers from different applications from different customers on the same physical hosts because virtual machines were isolated well enough to ensure that there's no undesired exchange of information or anything, or reduce noisy neighborhood issues so that the high utilization of one virtual machine doesn't really affect the other virtual machine too much. Which lowered the barrier of entry. As I said, customers could now get application clusters that were just affordable because they didn't have to pay for a dedicated service. Now, with an increased number of virtual machines, because we sliced our physical service into virtual service, there's an increased number of operating systems you have to handle, and you have to manage the lifecycle of more virtual machines. That's more effort. So this creates an automation pressure. You need to add more automation, otherwise you wouldn't be able to handle the resulting system complexity. And this is when we've been very strong in the Ruby community, or very tightly we've been using very much Ruby and Ruby on Rails at the time. So Chef was a tool appearing very, Chef was very, it was the obvious choice for us. We've done some experiments with Puppet as well, but finally I've chosen to use Chef. Now with Chef, the focus is about configuration management, and at that of course Chef has evolved too, but at that time Chef assumed that there's a running machine, and you can configure that running machine regardless of whether it's a physical or virtual machine. So it allowed us to centralize the operation of Postgres and other system services that we needed to provide to our customers. Very effectively, it allowed to reuse automation code more efficiently than shell scripts, for example, which also means that we increased the coverage of lifecycle management of Postgres quite a lot. There was less code duplicity, there was less necessity to document how-tos in Wiki because it was basically documented in the Chef cookbooks. So that was making a difference for us, and it increased the system availability because things were more reliable. It allowed us to manage more assets. Postgres at that time, we started to use asynchronous replication as it has basically turned out to be the best option if there's no strong case for synchronous replication. For example, it's the best all-round approach. It's stable even if there's fluctuation in network performance, or even if there are temporary network interruptions, let's say because a switch is being maintained or something. So that was just asynchronous replication is just proven to be the obvious choice, the default choice, so to say. So Pacemaker did work, but later we found out that Rep Manager just does a better job in handling particular situations, and we use that, and we still use Rep Manager for certain products. So if you think about building application systems, distributed systems, so we've been running distributed web development applications and manage them for our customers, then slicing up application servers, that's easy. But we started providing shared redundant, highly available Postgres clusters with our customers. And we started with physical machines. And the problem with physical machines is that there are certain resources within Postgres and certain configurations that will impact other users of the database as well. So, for example, the way the cache is used. So, well, first of all, at that time, with a limited number of customers, it was still possible to use shared database clusters and share them with multiple customers. And virtualizing those database clusters allowed us to create, cheap, dedicated clusters for our customers. And the learning here was that in general, those clients who are big enough to afford at least virtually dedicated database clusters are the ones that we have the least problem with, because there's a clear contract, meaning that they get amount of resources for the database clusters, and that's the amount of resources that they can use. They have that particular cluster for themselves. It can be configured in the particular way they want it, with those options enabled and those add-on enabled that they want. And whenever we change something, it is only their database cluster that's affected. So the takeaway here for us was that these dedicated clusters are much easier to manage in the interest of the client than it is the case with shared clusters, where you'd have to be more willing to compromise. So in general, at that time, using Chef, we found ourselves in a situation where the team couldn't handle more workload. So we tried to figure out why this is the case, which is not always that obvious, because the problems show from various different places. And at first they look like random events. But over time, you get a feeling that this is not the case, that there's an underlying problem. And one of the biggest problems is state drift. So, well, back in the days, when you order hardware servers in a data center where physical networks are being configured for you, and you do that multiple years, you don't have only one server, you have several servers. So there's a certain heterogeneity in the hardware landscape you're building. And servers age over time, and the heterogeneity, including with increasing probabilities for failure, that introduces, let's say, factors that will influence the availability of your system and will make things more complicated. However, there's also just a phenomenon, which is if you run automation like a lot of times, and back at that time, servers were meant to long for a long time. So they were running for months or even years, and you'd have to perform operating system upgrades. So there were things being done outside of Chef that will potentially influence the state of the machine, and then create a deviation from the assumed state, which is implied in the Chef automation. So basically, that's state drift, which means that the Chef automation assumes a state that isn't really there. These prerequisites aren't met, and consequently, you'd see failures in configuration managements, and you'd have to manually fix that, which takes a lot of time. So that increased unpredictability really disturbs the progress within the team quite a lot. Also, managing physical hosts, including host-focused and host-centric virtualization, like if you put together a network of manually managed or semi-manually managed Zen hosts, at some point you just drown in infrastructure work like the management of the network and all that. So it became obvious that building our own virtual infrastructure based on Zen, for example, is limiting because it is much more effort than initially anticipated, and it doesn't really scale well. At least it doesn't for smaller teams. So the team's utilization increased, and also training new members is hard because you need a lot of expert knowledge and you need a lot of contextual knowledge still to operate these systems. So the game changer for us was, in one sentence, the on-demand provisioning of dedicated Postgres instances based on declarative automation. So there are several steps to be taken to get there, but in one sentence, this is the key ingredient when things took off and we've been able to manage a multitude of assets per DevOps than before. So declarative automation, there are several technologies that you could be using. So we are using BOSH for virtual machines and Kubernetes for the orchestration of pods. And as we will see a bit later, it is also about the question and who manages service instances. So who has the operational responsibility? And for example, in BOSH, which comes from the Cloud Foundry ecosystem, there's also the Open Service Broker API, which is a RESTful API standard that your service broker, your automation, so to say, will need to comply to, and you can then integrate your data service automation with Cloud Foundry or any system that's you just provide an API to create service instances. So it's not that you have to have a sysop or a DevOps creating databases, but you can allow your application developers to do so. In Cloud Foundry, that's quite common. In Kubernetes with CRDs and operators, that becomes a obvious pattern as well, which is really good to see. We've been doing BOSH-based automation since 2014, and it took until recently that the Kubernetes community picked up that pattern and started making it more popular. So the shift in operational responsibility from operators to application developers is a key to also increase the number of assets that can be managed. In order to get there, you need virtual infrastructures, which basically means a programmable data center. So give me virtual machine, give me block storage, attach the block storage to the virtual machine, and so on. So dealing with state is for the operations of databases, very, very important, obviously. So the question is, where do you store it? And if you look at modern infrastructure, you don't store the data, on the virtual machine itself, because you know that those virtual machines are ephemeral. They could go away anytime. They're not very reliable, or they shouldn't be. But still, you would like to have a safe place to store the data of your Postgres database. So maybe even the single most important paradigm shift when you think about virtualization is not only that you provide everything through an API, but also that state is stored on a remotely attached block device, a so-called persistent disk, or in Kubernetes a persistent volume, where there's a storage server that's highly tailored to that specific task. It provides a very high durability, and your ephemeral virtual machine will mount that particular disk, and therefore you are flexible on where to locate your virtual machine, because your data can be mounted wherever you need it. And it decouples the lifecycle of your data from the lifecycle of the virtual machine, making the virtual machine disposable. So I will refer to this paradigm as the ephemeral VM persistent disk paradigm. And it's heavily used by Bosch, for example, and consequently, it creates predictable and repeatable deployments with very little state drift. So if you think about Chef and the idea that you have configuration management that will be triggered and executed when the virtual machine comes up, providing a certain amount of context information and then loading the automation and executing it, that's fine. But it basically does not take advantage of the ubiquitous presence of virtual infrastructures by design. So that's different with BOSH. In BOSH, it is a prerequisite to have such a virtual infrastructure, such as with the Kubernetes operator. It is a prerequisite that there's a Kubernetes cluster. So if you take the virtual machine as a necessary part of your automation, you can do really, really funny things that make automation repeatable and predictable. So what it means is you create virtual machines, and these virtual machines, they'll start from a well-defined virtual machine image, and then you run automation. So it's in that regard, it's similar to what Chef does, but the difference is basically that it is declarative by design, and that you reassemble the virtual machine throughout the lifecycle management inherently and by design several times. So you don't expect the virtual machine to run a very long time. So for example, if you would like to perform a vertical scale out of a virtual machine, you would just destroy it, create a bigger virtual machine, and reattach the persistent disk, and there you go. So Bosch makes that paradigm of the ephemeral VM and the persistent disk an integral part of lifecycle management, exactly like Kubernetes does. So, and that paradigm is what makes the difference. So if you think about Postgres at the time, there are new cluster managers such as Petroni coming up, very interesting, but still asynchronous streaming replication, at least for us, is the default if there are no context-specific requirements that suggest other strategies such as synchronous replication. Of course, if you think about lifecycle management and you would like to have application developers, hold the operational responsibility, then you also need to provide them with good backup and restore strategies. So implementing logical backups and point-in-time recovery backups is something that's very important among other features you need to provide. So you could call it a new stage because container infrastructures become very popular from the abstract perspective. As I elaborated earlier, the idea of having the ephemeral compute, your virtual machine or your container, and storing the state somewhere on a remotely attached block device. I mean, that's what Kubernetes does as well. And if you think about Kubernetes operators and Bosch deployments, they are on that level very much alike. Of course, there are also many differences, but if you ask me, they are similar in the amount of assets you can manage per DevOps. I see some advantages for Kubernetes. I also see some advantages for Bosch, which are sadly beyond the scope of this talk. But I'd say, well, Kubernetes is the obvious choice to do container orchestration these days. It also provides a declarative automation approach. It becomes kind of the infrastructure abstraction API of these days. So Kubernetes is ubiquitous nowadays. You're everywhere on every infrastructure, on-premise as well as on public infrastructures. You can get a Kubernetes cluster. So it also becomes interesting for the automation of Postgres. So there are already several Postgres operators you can choose from, including the one that we provide. So Kubernetes is more than just an orchestrator or scheduler for containers. It becomes an open framework for cloud automation. Now there are some issues with Kubernetes. Because often Kubernetes is used as infrastructure abstraction, which means in the end you're scheduling virtual machines again. So consider you have an environment where with a rapid growth rate, you are adding more Postgres databases. So we have environments where within a year 500 database clusters have been created, and each database cluster is represented by a dedicated set of virtual machines or pods, and you need to put them somewhere. So where do you put them? Do you put Kubernetes directly on physical machines? Well, you can do that, but most of the cases I've seen, there's a virtual infrastructure underneath. So there are virtual machines, and while with Bosch you could use all the virtual machines by just tell Bosch to create more virtual machines in Kubernetes, you cannot just add more pods. But at some point you'd have to also create more Kubernetes nodes that are suitable for holding those pods. And if you co-locate pods on Kubernetes nodes, you may run into noisy neighborhood issues because the isolation of the average pod, at least the average container, runtime, is not as high as with virtual machines. So the management of the Kubernetes cluster becomes an issue because you may have to add Kubernetes nodes on demand in order to provide a target for the pods to be scheduled, which with a deviation boils down to on-demand provisioning of virtual machines, which is basically what you can also do with Bosch. So I'm not a Bosch fanboy. I'm just pragmatic in the way that I think both tools solve similar jobs. There's definitely more publicity around Kubernetes these days, and therefore there's value in using Kubernetes. That's why we also use Kubernetes a lot. But on the abstract level, they are very much, alike and solving similar problems. In our container-based products, we use Petroni as a cluster manager because it is more flexible than Red Manager. It has certain advantages. Both work very well, also at scale. So when I talk about scale, I mean the thousands of service instances. And over time, Postgres becomes more friendly for automation. So including version upgrades, the ability to run binary upgrades that are rather simple to orchestrate in a distributed cluster with replication, so that you don't have to execute scripts depending on the role of individual nodes in a cluster in a timely, ordered manner, makes the lifecycle management much easier. So what's the future? Well, I would say, covering more of the life cycle is just something that needs effort and time to develop on how to approach it. I think the paradigms necessary are already there. The idea of on-demand provisioning of dedicated instances as the single most paradigm, which relies on the idea that there is a programmable data center underneath, whether this is scheduling virtual machines or pods, doesn't really matter. In combination with the declarative automation technology, those are the things needed to get to this idea of having application developers managing their own databases without the necessity to become database experts. There's a lot of room for improvement, including dynamic configuration of databases, validating configuration changes regarding whether they really make sense. And I think there's room for artificial intelligence on consulting application developers with expert reasoning on configuration changes. For example, telling them, well, it doesn't make sense to have a Postgres instance that has that amount of cache in, let's say, a pod that only has that amount of memory. So I think there will be, many years to come to get to that full lifecycle management to the fullest extent, and I'm very looking forward to see what's coming. So to sum it up, we've been using in the past decade several different approaches, starting with imperative technologies or approaches such as shell scripts, then using Chef. Gradually, the introduction of virtualization allowed for technologies that will do lifecycle management of distributed systems more comprehensively, such as BOSH and Kubernetes. The declarative approach, where there's an agent trying to reach a desired state, over the more imperative approach, where you execute a particular set of instructions, has proven to be a large step in the right direction, which allowed us to increase that amount of assets under management per DevOps significantly over time, which is obviously very beneficial also for the profitability of a company. So that's basically our story, and hopefully, this puts things into perspective, especially for cloud engineers and people who want to do Postgres automation and maybe haven't been in that community for the past 10 or 15 years. So if you really want to boil it down, in my opinion, it's a success story of virtualization, especially the ephemeral VM and persistent disk paradigm, the upcoming of declarative automation, and the increased friendliness of Postgres to be automated. So hopefully there's something you took away from today's talk. Hopefully see you next time. Thank you very much for your attention, and bye-bye.